Hi. Now, you may think that as an engineer, studying 1 degree of freedom system is a little bit simple. Well, actually, you're not going to design a mass on a spring. Well, we're going to see in a dedicated video that it's actually possible for any type of structure to reduce it to the combination of 1 degree of freedom systems. But there are structures for which it is a little more obvious how to do that, and let's take a look at that first. The first example of a structure that can be modeled with a 1 degree of freedom system is represented here on the left. So consider that you have the first level of a building made of a rigid floor and flexible columns. These flexible columns can be represented by a spring, and the rigid floor is represented by a mass. The whole system is excited by its base, the ground motion due, for example, to an earthquake. A second example is a rotating machine represented here on the left, and in this machine you have the rigid stator plus rotor represent a certain mass, m, and they are put on a flexible foundation, so with flexible mounts, and these flexible mounts are modeled with a spring K. The rotor imbalance, when the system is rotating, creates a force that is acting on the mass here. A third example is a car. If you consider that this car only has a vertical motion, you can represent the body of the car by a mass, or a rigid body represented by a mass, and the suspensions here are represented by the stiffness K. The road irregularities are creating vibrations inside the car, and this is represented by the motion here of the foundation. A fourth example is this offshore platform, where you see that most of the mass is on the top here, and this is then modeled by a mass m, and the foundations are flexible, represented by a stiffness K. The waves, when they are hitting the platform, are applying a certain force, which is represented here by f of t. In order to study the vibrations of a single degree of freedom system, it is important to understand what is harmonic motion and the associated mathematics. Let's watch this video as a first introduction to simple harmonic motion.
Professor Dave here. Let's discuss simple harmonic motion.
He knows a lot about the science stuff. Professor Dave explains.
Sometimes when we examine the motion of an object, it will involve a single action, like a rock falling from a cliff down to the ground. This will probably just happen one time, after which the rock will remain at rest. But some motion is periodic, meaning repeated, like the motion of the pendulum on a grandfather clock, or the vibration of a spring. We will refer to this kind of motion as simple harmonic motion. Say we have a spring that is attached to some stationary surface, and on the other end of the spring there is a block of a particular mass. If we pull this block so as to expand the spring, and then we release the block, it will vibrate back and forth between more compressed and less compressed states. If we assume that the surface of motion is completely frictionless, then the elastic potential energy reaches a maximum when the spring is most or least compressed and the block is changing direction, while kinetic energy is at a maximum when the block is right in the middle and moving the fastest. If we were to graph the position of the block against time, it would display sinusoidal behavior, just like a trigonometric sine function, where the block continues to occupy the same positions over a particular period of time, which is why we call this periodic motion. X equals 0 at the equilibrium position of the block, where it sat before we pulled it, and assuming 0 friction, the block will oscillate between positive x and negative x indefinitely. In reality, frictional forces will dampen the spring's activity, and it will eventually come to a stop. But for many systems, an ideal mass spring system will be a decent approximation for a real one. Of course, every spring is different. Some are loose, like a slinky, and some are stiff, like the spring that launches a pinball into play. This factor is represented by the spring constant K, which will be unique to a particular spring. The force that a spring can exert is equal to negative K times the displacement of the object it acts upon, and this relationship is called Hooke's law. The negative sign indicates that the force of the spring is always opposite the direction of the movement of the object. When the object compresses the spring, it will push out, and when the object stretches the spring, it will pull in. In both cases, the spring is attempting to move the object back to its equilibrium position, which is why the force applied by the spring can be called a restoring force. The units on a spring constant will be newtons per meter, so that when you multiply by some distance x, you get the force that must be applied to compress that spring that far. Let's also note that the elastic potential energy of a spring will be equal to 1/2 kx squared, where k is the spring constant and x is the distance it is stretched or compressed. If at equilibrium, the distance is 0, so it has 0 elastic potential energy, and the maximum elastic potential energy will occur at the maximum distance from this point on either side of the oscillation. This expression looks similar to the expression for kinetic energy, which is convenient since the two will interchange as the mass oscillates. A pendulum also displays periodic motion, since it swings back and forth between the same two positions. Although this involves gravitational potential energy rather than elastic potential energy, and we will look at this behavior next.
Harmonic signals are periodic signals of which the amplitude can be described by a sinusoidal function or a cosinusoidal function of the form given here, where the amplitude is A. The frequency, the angular frequency, is omega, which is equal to 2 pi times the frequency, and omega is expressed in radians per second. The frequency f is expressed in hertz, and so the period is 1/f. The phase angle, phi, is the angle at t equal to 0. The total phase angle is omega t plus pi. We are going to use a representation of these harmonic signals in the complex plane. So it consists in writing your signal u of t as an amplitude, a real amplitude, multiplied by an exponential with an imaginary exponent. We know from trigonometry that this expression is equivalent to a real part made of a cosine function and an imaginary part made of a sine function. Now, if we decompose the signal with the time-independent part and the time-dependent part, we can define this complex amplitude capital A, which is equal to A cosine of phi plus I A sine of phi. And so this is a complex number that does not depend on the time anymore. If we want to represent A in the complex plane, we have here the real axis and the imaginary axis. A is here with an amplitude small a and a phase phi. Now, as you increase the time, you see that the vector is rotating around the circle so that its projection on the real axis is a cosine and the projection on the imaginary axis is a sine. What is the advantage of this representation? It is that if you want to compute velocity and acceleration, which are first and second derivative with respect to time of your signal, then you simply have to multiply for v by I omega and then again by I omega, so in total by minus omega squared to get the acceleration. So what it gives in the complex plane is that you have your initial vector A. When you multiply it by I omega, you have a change of phase of 90 degrees and an amplification by a factor omega. And when you multiply it again by I omega, you have a total amplification of minus omega squared and a phase shift of 180 degrees. Now, if we project this on the imaginary axis, you will see that u of t is a sine function of amplitude a, v of t is a cosine function with amplitude omega a, and a of t is a minus sine function with amplitude omega squared a. Let's see that now in image. You will see that here When the displacement becomes 0, the velocity is maximum, and the sign of the displacement is opposite to the sign of the acceleration. What is important to understand here is that in real life there is no signal that is imaginary. A displacement, a velocity or an acceleration are always real quantities. So really what we are using is a mathematical trick in order to solve the equations in a more easy way. So imaginary numbers do not represent imaginary quantities. They actually contain two informations: the amplitude of the signal and the phase of the signal. Now that we have understood what is harmonic motion, we need to move to some mathematics to better understand what will be the level of vibration of a 1 degree of freedom system. First, we focus on systems without damping. If we consider this simple mass spring system without any damping in the system, that is excited by a force here at the bottom. Newton's law tells us that the mass of this body times its acceleration is equal to the sum of the forces applied to the body. The first force applied to the body when you are in motion and there is a certain motion x which is seen positive in the upward direction, you see that the force that will exist in the spring is opposite to this direction and of amplitude kx. The second force acting on the body is F, which is in the same direction of x here, so with a positive sign. And so in total, if we put everything that depends on x on the left, then we get the equation of motion, which is m times accelerations plus k times displacement is equal to F. Now, what about the effect of gravity? So gravity is acting on this body. Well, if you look at a spring, you have the length L0 when the spring is not stretched. Now, when you add a mass to the spring, you will have a certain stretching of the spring, which is delta L. And in fact, because the body is in equilibrium, K times delta L is equal to mg. So the force of gravity is compensated by this initial stretch. Now, what we are looking at in dynamics is the motion of the body with respect to this equilibrium starting position, so that gravity does not have to be taken into account because it's already compensated by the spring, the force when the spring is elongated. Now, first we're going to look at free vibrations. So free vibrations occur when there is no force acting on the body. Think, for example, you are pulling the mass downwards and then releasing it. What will happen? Well, in order to solve the problem, we assume that x is equal to an amplitude a times e to the power of rt. And this leads us, by replacing in the equation, to the characteristic equation mr squared plus k equal to 0. So a solution exists to this problem if r satisfies this equation. And the solution is r is an imaginary number. It can be either plus or minus I square root of k over m. So if we replace this r in here and we take into account trigonometric relations, we can show that x is the sum of a cosine function plus a sine function, where the frequency omega n here is given by square root of k over m. The constants a and b are not known, and actually you need to give the system some initial conditions to know how the vibrations will be. These initial conditions are in the form of an initial displacement x0 and or an initial velocity x dot 0. So that if you take these two into account, x of t is given by the expression here. And let's take the example where the initial velocity is 0, so you are pulling on the spring, giving an initial displacement x0 and then releasing. In that case, you see that you will only have a cosine function of this type. So the mass will oscillate with a cosine function with time, where the frequency of this signal is given by omega n, which is square root of k over m. We can use an alternative representation of that. So again, using trigonometry, you can write this as a single cosine function with a frequency omega n and an angle phi. And by equating these two, you can see that in the end, this initial angle phi is given by the velocity, initial velocity, divided by omega n x 0. So that if the initial velocity is 0, this initial phase is 0 as well, and we have a cosine function. If we now consider that the force applied to the body is not 0, but is an harmonic force of the form given here above, then we know, because the system is linear, that the response will be in the same form. We can plug these into the equations of motion, and we get the following expression. You can see that then you can just cancel the two terms depending on time, and you have an expression which gives x, the displacement of the mass, as a function of the force and the forcing frequency. So this is the frequency of the force that you apply. This term can be simplified by looking first at the displacement at 0 frequency. So if we replace omega by 0 in this expression, we get F over k, which is the static response. This is how much the mass will be displaced if you put a static force on the spring. Knowing that the natural frequency is square root of k over m, we can rewrite this expression to find the ratio between the displacement of the body when you excite it at a frequency omega and the static displacement of the body. This ratio is positive if omega is smaller than the natural frequency of the system. It is infinite if the frequency of excitation is equal to the natural frequency of the system, and it is negative if the excitation frequency is higher than the natural frequency of the system. Now this factor, the 1 over 1 minus omega squared divided by omega n squared, is a dynamic amplification factor. It represents by how much the displacement is amplified when you are exciting at a certain frequency rather than statically. And so this dynamic amplification factor can be represented in a Bode diagram, where the x-axis here is the frequency of excitation. So here it is normalized by the natural frequency of the system. And on the y-axis we are looking at the amplitude of x over x0. So you see that when omega is equal to 0, of course x is equal to the static response. So this is 1. And before the natural frequency, this term is positive, which means that the force and the displacement will be in phase. At the natural frequency, this term tends to infinity, so you see that you will have a very high amplification of the displacement. And when you have an excitation frequency higher than the natural frequency, then you can see that the phase will be opposite between the applied force and the displacement. These equations show us that if you excite a 1 degree of freedom system as a specific frequency, which corresponds to its natural frequency, then the motion will go to infinity. This specific phenomenon is called resonance, and we're going to illustrate it with some movies. This first example illustrates the fact that you can break a glass with your voice using resonance.
Yes! All right. Yes! Glass number 90. And that's proof that it's not a trick. That was too easy, man. Number 93. That's 5 today.
Now let's look at that with a more scientific perspective. In the first step, we're going to analyze the glass to know what is its resonance frequency. So you hit the glass, you measure with a microphone, and then you perform what we will see later, which is a Fourier transform. Based on that, you can see here some peaks, so some amplifications around 630 Hertz. So now we're going to use an excitation which makes the glass move at that frequency. The straw that you put in the glass shows that there is motion, but not enough to break it. And the stroboscopic light is used just to show the motion in a more slow motion, to make the vibrations visible. Now if you put a higher volume, well, you can break the glass because you excited it exactly at its natural frequency. So you see how the glass is vibrating, and then vibration builds up and eventually it breaks. Now resonance can also happen in buildings, and the question we're asking here is it better to build a stiffer structure against vibration? So if you take these two things here that represent a building, well, this one is shorter, so obviously it's stiffer. And is that going to be stronger against an earthquake?
So did you make your predictions? So earlier we found that these two different buildings will respond differently as I move them. Okay, but what's going to happen when an earthquake comes? I'm guessing a lot of you said this taller building would be most affected. It turns out I can make the smaller one be most affected. Okay, but that was just one type of earthquake. You can also have a different type of earthquake that causes the taller one to be most affected. So the answer is it depends. Okay, so it depends upon the input motion. So a higher frequency input motion. So if I'm oscillating this more quickly, it's going to affect my shorter building, as opposed to a longer frequency. Okay, then I'm going to affect the higher, taller building. So what's happening? Okay, it turns out earthquakes don't have a single frequency of input motion. They don't oscillate back and forth in a nice sinusoidal fashion like I'm trying to do. But they do tend to have a predominant frequency. So they'll have a predominant frequency that's either fast or slow. A lot of that is dependent on the soil conditions. And what's happening is something called resonance. So as my input motion matches the motion that my building wants to oscillate at, I set up what's called resonance.
Another example is given here. So you see that the system on the left is smaller, and so it is stiffer, and the one on the right is less stiff. So the system is going to be excited from the bottom, and the frequency of excitation will increase. So because this system here is less stiff, its natural frequency is lower because the masses are the same. So the first that will be affected by resonance will be this building, and then this one, and then this one. So the frequency is slowly increasing. You see some vibration initiating, and clearly you see that now that you are building resonance in the first system, the one on the right. And so clearly you will see it more and more that energy builds up in that system, and it will lead to very high amplitude at a specific frequency, which corresponds to the natural frequency of this first single degree of freedom system, given by square root of k over m. Okay, so here you see really the resonance building up, and this is at a frequency of 4 Hertz. then think about the boat diagram. When the frequency increases, now the motion will start decreasing as we go away from resonance. We are still close to resonance, but you see that the motion is decreasing. And as this motion is decreasing, you see that now the resonance is building up in the second system. So there is more motion in the second system, and you see that it happens at a higher frequency than for the first system. The resonance is at 6.35 Hz. And now you understand that if we continue, you will have the same with the third system at a higher frequency. Another illustration of the importance of the natural frequency of structures when you have, for example, a ground motion due to an earthquake.
When we see this kind of picture, it's a Mexico earthquake, we see that small buildings collapse and not high buildings. So it's a real problem. And what kind of problem is? It's a problem of resonance. So buildings resonance. So to understand this phenomenon, we can make this experiment with the same screwdriver, automatic electric screwdriver, with an eccentric here. And this system we can switch on, off, and also increase the speed. We have different building of different height, and I'm going to make the system working to show to understand what is the resonance phenomenon. So with this system, I can increase the speed and nothing appears because the eccentric is not far from the axe. So now I am putting this far, and now I see the beginning of the working, this system working. So now I'm going to study the resonance. We can see that the big buildings resonates. I'm increasing the speed. And now, yes, the big building, and now the intermediate building resonates. And I increase again, and I see the small building resonating too much and no foundation, so small buildings collapse. Maybe exactly like that, but it's not a problem of foundation. Here it's a problem of size of building.
Now, motion will never go to infinity, and this is because in any real system there is always some dissipation and so some damping. So we need to study also the response of a single degree of freedom which contains damping. If you add damping to a building, what will happen? Well, you see that if you give an initial displacement and release, the first building is moving and vibrating while the second one is not. And if you are doing a base excitation, you also see that the first building, which will be much more subjected to vibrations. Now, if you look at the equations of motion, adding a damper, which is represented here by a dashpot with a constant b, results in an additional force, which is also opposite to the motion and equal to minus b times the velocity. And so in the equations of motion, there is an additional term bx dot. Let's first rewrite the equations of motion by defining a damping coefficient psi, which is equal to b over 2 square root of km. So we divide this equation by m, and we find here, for example, k over m, which is omega n squared. And so the equations of motions are now written in this form, where you see the natural frequency omega n and the damping coefficient psi. Now, if we look at free vibrations, which correspond to the case where the force is zero, and look for a general solution of the same kind as for the undamped system, then the characteristic equation has an additional term, 2 psi omega n r, and the solution of that, if you consider that psi is smaller than 1, and define omega d as omega n times square root of 1 over psi squared, you find that R has also two possible solutions, but now there is a real part, minus psi omega n, and an imaginary part where the frequency is not omega n, but omega d, given by omega n times square root of 1 over square root of 1 minus psi squared. And if you look at the response in the time domain, you have the same as in the undamped case, but the frequency again is slightly different. But also you have an exponentially decaying envelope e to the minus psi omega n t. If you give initial displacement and velocity, you can find the values of A and B, and this is the result. Now for an initial displacement, if you have free vibrations with zero damping, we saw that then the motion is a cosine function and it continues to vibrate forever. If you put a small amount of damping, so this is 1% of damping, you see that the vibration will decay with time. And if you increase more and more the damping, you go to 5 or 10%, you see that the motion decays faster. Actually, it's good to have a look at orders of magnitude. If you plot here in the log scale the value of damping and here the number of oscillations that are necessary to reduce the vibration by half with respect to the initial motion, you see that for 1% you need 10 cycles to reduce by half. Whereas if you have 10%, then you only need 1 cycle so that the amplitude is reduced by half. Now, if psi is bigger than 1, then the expression is different. And if psi is equal to 1, it is also different. And it is actually called critical damping. But let's look at what it means in terms of response. So if you give an initial displacement and you have psi is 10%, then you see that you will have oscillations. Note that after one oscillation, the amplitude is reduced by about half. If you have critical damping, then in this case there is no oscillation and the system comes to zero very fast. As you still increase the damping, the system will not oscillate but will come to zero later. And if you have very high values of damping, it's as if the dashpot was so strong that it blocks the motion and the mass remains at the initial position. So in this course we're going to be interested only in values of psi smaller than 1 because this is when you have oscillations and therefore vibrations. Now that we have looked at free response, we're going to look at forced responses, and the first one is a very typical one called impulse response. An impulse response is the response to a very short force applied to the system. So we consider here a force F that is applied for the system for a very short time delta t, and then no force is applied anymore. We start from a system at rest, so with zero initial displacement and zero initial velocity. If we integrate those equations, we have on the left m times the velocity at times delta t, because the velocity at time 0 is 0, which is equal to f times delta t, so the integral of f over this time, minus these two terms. And now we're going to do the hypothesis that because the initial displacement and velocity are small, and because this time is very small, these two terms can be neglected. So what this means is that if you apply an impulse, it's equivalent to apply an initial velocity at time delta t, which is equal to f delta t, the value of the impulse, divided by the mass. So for an initial velocity, we know that the response of the system is in that form, so it will be a sine function. By replacing this initial velocity by the value of the impulse, and by defining the impulse response as the response when f delta t is equal to 1, then we can get to the value of the impulse response, which is given by an exponential decaying function times a sine function divided by m omega d. So as you see here, this is a typical representation of such an impulse response, where if you have a natural frequency of 1 and a damping factor of 1%, you will see that it will oscillate at frequency omega d, which is very close to omega n, because the difference is 1 over square root of 1 minus xi square, where xi is very small. Now let's look at harmonic excitation. We make again the hypothesis that x of t and f of t can be expressed as a complex number times a function of time, which is e to the power of I omega t, and we replace in the equation of motion. Then we solve for x, and this gives us the following expression, where we then substitute omega n squared here for k over m, which gives us a f over k, and so in the end we can get the same result as for the undamped system, which is to express x as a function of x0. And you see that you will have a real part and an imaginary part this time, and the imaginary part is due to the damping term. Remember that when xi is 0 for an undamped system, we only have a real part that can change sign. So the expression here is now a little bit complex. It is actually a complex number, and this complex number, we should look at its amplitude, given by the expression here, and its phase, given by the expression here. Now this is represented in a Bode diagram, where here, because we have damping, we will represent both the amplitude and the phase. So the graph shows that as you increase the damping in the system, the maximum amplitude at the natural frequency, or close to the natural frequency, will decrease. Actually, this maximum occurs at omega over omega n is square root of 1 minus 2 xi squared. So it is close to the value of omega n, especially when the damping is small. And the maximum amplitude is given by this expression. For small values of xi, the maximum occurs at the natural frequency, so when omega divided by omega n is 1, and the maximum amplitude is given by 1 over 2 xi. It means that if you double the damping, you will reduce by half the dynamic amplification at resonance. If we look now at the phase, you see that when a system is not damped before resonance, you are in phase. After resonance, you are out of phase. But now, as your damping increases, you see that the transition between these two regimes is softer. At resonance, you always have 90-degree out of phase motion, but this occurs gradually from 0 to 90 degree when there is some damping, and then from 90 to 100 degree as well. So as stated, you know that displacement is given by an harmonic function. Velocity is I omega times that, and the acceleration is minus omega squared times u. So that means that if you plot the Bode diagram, you see that for displacement you start from the static response, and then you have a decrease after resonance. For velocity, you will start from 0 because you are multiplying by I omega, so omega is 0 here. And you see that velocity is increasing until resonance and then decreasing. For acceleration, it is still 0 at 0 frequency, but after resonance, it tends to a certain asymptotical value, which is non-zero. We have seen how to solve the equation of motion for three particular cases. The first one is free vibrations, and the two others are related to force vibration, where the force is either harmonic or an impulse. But what happens if the force has a different expression? Now, not all systems are excited by an harmonic force or an impulse. The force applied to the system can take any arbitrary form as shown on the right here. In this case, f of t can be decomposed into a series of short impulses. And the contribution of each impulse, as shown by the gray box here, to the response of the system is given by f at times tau, times delta tau, times the impulse response that is shifted by a value of tau in time in order to correspond to this point in time. Now, because the system is linear, the total contribution is given by the integral of the contribution of all these boxes. And so it is the integral from 0 to t of f of tau h of t minus tau delta tau. Because h of t, the impulse response, and f of t, the excitation force, are equal to 0 for time smaller than 0, we can extend this integral from minus infinity to plus infinity, which actually defines a convolution integral marked with the asterisk here. So what is a convolution integral? The convolution integral of two times function, x of t and h of t, yields a new function, y of t, which is given by this integral and noted with an asterisk. So in practice, you take two functions, x and h, and replace t by tau. Then you can mirror function h of tau to yield h of minus tau, shift this function with the quantity t to get h of t minus tau, and then for each value of t, you multiply x of tau by h of t minus tau, and you compute the integral. And by varying tau from minus infinity to plus infinity, you have the final function. So let's look at an example. We have the first function, which is a square of length 1 and height 1. We have a second function that is half of that, and if we mirror it, then it goes to the other side of the axis. Now we're going to shift it in time and compute the integral of this one multiplied by this one. So what does it give? If you look at very small values of time, then these two rectangles don't interact, so the product is always 0. But as soon as they start interacting, you see that you will have a certain value of the integral when you multiply the two functions. Here, for example, it is given by the gray box. Actually, the resulting function will increase linearly until the maximum where the two boxes are matching as here, and so the area is maximum. Then as you continue shifting your function, you see that the area will decrease again and go to 0. So in the end, you have taken two rectangular functions, and by convoluting them, you have obtained a triangular function. There is a property which is that if you convolute x with h, it is the same as convoluting h with x. Let's illustrate the use of Duhamel's integral on a simple 1 degree of freedom system where the stiffness is k, the mass is m, and the damping is b. So it is excited by a force here, and let's first consider that the force is given by a sinusoidal, so harmonic excitation, and the frequency of this excitation is well below the resonance frequency of the system. So you see here the impulse response of the system. The ratio of the two frequencies is 10 and the damping is 1%. When you convolute these two functions, this is the result that you get. So you see that it looks like a sine function, but in the beginning you have a transient regime where it is not a pure sine function. After that, in the steady state, you have a sine function. So basically, when you're looking at a Bode diagram and you excite at an harmonic with an harmonic force, this part, the steady state regime, represents what will be the amplitude and the phase of the signal of the response. But note that there is always a transient regime where the output, the displacer, is not purely at that frequency. Now let's look if we are exciting near the resonance, so now the ratio of frequency is 95%, so we are close to but still below resonance, and this is the result that you see. What you observe on this is some beating phenomenon that occurs in the transient regime. So you have established regime here, but in the transient regime you see that it seems to be a second frequency that is due to the fact that two frequencies, the one of the excitation and the one of the natural frequency of the system, are very close, and this leads to a beating phenomenon in the transient regime. If we excite the system exactly at resonance, so now omega over omega n is exactly equal to 1, in this case you see that there is no more beating because the two frequencies are the same, and that after a certain time it reaches steady state. Now, if we change the damping, so this is the initial damping of 1%, if we change the damping, for example, to 5%, what happens? First thing that you see, and this is something we discussed, so when the damping is small, if you multiply the damping by 5, because the amplification at resonance is 1 over 2 psi, the amplitude of the motion will be reduced by 5, and this is what you see here. But what you also see is that the time to reach the steady state is much shorter. Here we had about 400 seconds, here it is reduced to 100 seconds. So the motion is less, but also the time to reach the steady state is less. What happens if you excite above the resonance? So now we are using a frequency of excitation that is twice as large as the natural frequency of the Wand-Off system. In this case, what you see still is that there is a transient regime and a steady state regime, but you see that in the transient regime there is a high amplification really of the motion, and you really see these two frequencies that are present. So you have the frequency of the Wand-Off system and the frequency of excitation, which are both present in the transient regime. Now let's move to sine sweep excitation. What is a sine sweep excitation? You are basically using a sine function, but of which the frequency will increase with time. So you start at low frequency and then you increase it. Here we are going to swipe from a frequency lower than the natural frequency of the system to a frequency which is higher and look at the response. So what you see clearly is that at frequencies lower than the natural frequency there is a small movement. Then as you approach the resonance frequency there is amplification until the point of resonance, and after resonance the amplitude of motion decreases again. There are cases in which the dynamic excitation is not applied directly on the body but at its base. How do we solve the equation of motion in that particular case? In the case of base excitation, we are not looking at the case of a force applied on the mass m, but at the motion here of the support. So when the support moves by a displacement x0, we need to look at the equations of motion. So we have the mass times the acceleration, which is equal to the sum of forces, but now the sum of forces are proportional to the compression of the spring, which is given by x minus x0, and the relative velocity between the support and the mass, which is x dot minus x dot 0. So it is common when you want to look at this kind of problem to change the variables and consider only the relative motion. So this is between x0 and x, which leads to the following equation. So you see that this is the same equation as the Wand-Off system excited by a force, where the force is given by minus m times the acceleration applied to the basis. This video will illustrate the harmonic response of a mass spring system excited by its base.
First we will find the natural frequency of the system. To do this, I set the spring into motion and measure its response with the ultrasound sensor below. Then I do a sinusoidal curve fit on the graph in order to find the natural frequency. For the remainder of the video, we will excite the system below, above, and at the natural frequency to give an idea of the physical response. In this test, we drive the oscillator below the natural frequency. Notice that the top of the spring and the mass reach their maximum and minimum height at the same time. They are thus in phase, as can be predicted by the positive amplitude in the particular solution. Next, the system is driven above the natural frequency. Notice the spring seems to expand and contract, as the two ends are 180 degrees out of phase, as predicted by the negative amplitude in the particular solution. Finally, we will excite the system at the natural frequency. It's much harder to see, but the top of the spring and the mass are 90 degrees out of phase. Notice that the amplitude is very large and continues to increase. At a point, however, the spring compresses fully and it cannot gain a significant amount of amplitude. This assures that the amplitude will never actually reach the predicted value of infinity.
And if you want to compute the response to ground acceleration in the time domain, this is the typical example of the earthquake, then you can just combine what we have done before. So you know that the equation of motion has a force that is equal to the base acceleration of the earthquake, and you can use Duhamel's integral, where you do a convolution between the force, which is now given by this minus mx dot dot 0, times the impulse response. So if you replace by the impulse response of a one-off system and the force by minus mx dot dot 0, this is what you get. So the relative motion between the ground and your building will be given by this convolution integral. Let's look at an example. This is the recordings of acceleration multiplied by mass for the Santa Cruz earthquake in 1990. We are going to convolute that with the impulse response of a system that has now a natural frequency of 6 Hz and a damping of 1%. This is the result. So this really gives you the relative motion between the ground and the mass as a function of time when the earthquake hits the system. This is the end of the journey on single degree of freedom systems. Remember, the tools that you have learned in this video are very important as they are the foundation of structural dynamics.